should be good to go. All right. So everyone can see my presentation, not like my email window or anything?
Yeah, all good.
All right, excellent. All right, so I'm going to be talking about, so last session I mentioned, hey, there's this method called the consensus method that could be used to help estimate a wind speed. This is going to be based on some work Windesco did with NREL, focusing mostly on estimating wind direction. And so I have examples from a presentation, but then at the end I give an example on wind speed. And originally I had planned for 20 minutes. You had said, Florian, can't do it. Can I talk for a little bit longer? So I did add some perspective. The bigger picture of this meeting is to talk about how do we measure performance. So I just wanted to share some experiences and insights we've had from the industrial side, like working with customers, trying to convey effectively performance improvements. One of the things Windesco does is identify opportunities for customers to improve their wind farms, and then fix that and then measure that improvement. And the measuring part can be very contentious. When we talk with customers, they say, well, OEMs will upsell a product, and then the OEM comes in and measures the improvement and says, look, you got a great improvement. And there's a lot of challenging issues of trust, reliability, transparency with performance measurement, which is one thing that attracted me to this group, is if we can have an open source third-party-ish kind of measurement technique, that would be great for everybody. So quantifying improvements in performance is really hard to do for turbines in production. Issues we run into all the time are measurement inaccuracies, variations in turbine configurations, and also, as I mentioned, originally, the customer perception of improvements. And these are real challenges to overcome. And we find different levels of technical understanding and capabilities across our customer base. Some don't understand the details. They've bought a wind farm and they don't understand the technical details. Other customers are fantastically technical and we can have great conversations with them. Another challenge we have is, how do you get people to look beyond the power curve itself to see an improvement? You make a 1% improvement in region 2, it can be hard to see that in a power curve if you do a scatter plot of a power curve. So customers look at their power curve and say, it looks the same before and after. So the real challenge of this group is, how do you convince somebody that there's a change when it's not visually apparent through their traditional way of evaluating turbine performance? So I'm going to give some thoughts on that. And then the second half, I'll talk about this consensus method, which is a way to help estimate measurements at a given turbine using adjacent turbines, the measurements from adjacent turbines, to help weight that averaging. So I talk about wind direction from a previously published work, and I did a quick wind speed example. For that, really, you can use this for any signal. And even though we can do this and it's great, I still don't know how robust it is. There are limitations to it, but I think there's some, useful applications of this that will, I'll give the example for wind direction. So, the objective, what's our objective, is to operators and owners want to observe improvement in their performance after they make a modification, whether it's something we suggest, which is typically hardware, or they do some maintenance. We typically do software upgrades, but they might add VGs, things like that, or they do some maintenance. They clean the blades. Do we see things get better? They make repairs. They would like to see things get better. Some of the challenges, like from our point of view, is we want to have a nice clean experiment. You have a baseline for the turbine operation. We make a single parameter change, and then you have this data collection period where you try and optimize. But all too often we have things where either OEMs push software upgrades that change performance. The customers have to do maintenance. They aren't going to push off their maintenance so we can collect our data. So there's there are challenges with that. that make this even harder to do beyond the fact that it's a real world situation that just, if they make the change at just the wrong time, we have some sites where the winds blow from the east in the summer, west in the winter. If they make a change right in that transition period, your before period is winds from the east, your after period is winds from the west. It's not really a fair comparison. And often, as I'll repeat this a couple of times, operators just have a fundamental misunderstanding of how to observe performance improvements. Other challenges that we encounter, each turbine is unique in its configuration, aerodynamics. They may have different blades, different cleanliness, newer blades, older blades, things like that. The maintenance of the turbines may vary from turbine to turbine. Topography and meteorology can vary significantly from turbine to turbine, especially if you think of areas like California where they put all these turbines in the Altamont Pass. Really challenging area to do any kind of measurements. What we've found and how we try to approach this is just, we want to use no additional hardware. We're trying to do this fully SCADA-based, which means we don't want to recommend customers drag around LiDAR, which I think can be valuable. It's just makes it harder to change 20 turbines and get timely estimates for that. So our goal is to not use that. We also try to avoid using a Met tower just because they may be old, not well placed for the turbines we care about. And the other thing is, we have turbines that are laid out in a grid. So how do you measure performance improvement for a turbine in the middle? It can have waking conditions, which if you went by an IEC standard, we would ignore those, but customers you make a change, they want to measure an improvement. So there's additional challenges with what do you do with the turbine in the middle of a wind farm. We do use nacelle anemometry for some things. I like to view it skeptically, just because nacelle transfer functions can change. Either the anemometer's out of calibration or anything. I'm not saying don't use it, just be aware of the drawbacks of that. The other challenge we have is nacelle position measurements are often uncalibrated to north. And some OEMs have nacelle measurements that just drift. That the turbine's not moving, but the measurement itself will drift over time. They just don't have great control on the estimate of nacelle position. And that makes it challenging to say, well, we know this turbine's waked from the east, or we set an arbitrary position at 45 degrees. But if that keeps moving, we don't even know where it's waked anymore. The measurement standard, like the IEC standard I talked about, to follow that 100% is challenging in the field. But, there are things that we picked up from that make sense, density corrections, binning requirements for power curves, things like that. And just be mindful of the shortcomings that we have. So just from an industry point of view, this has been a challenge for us. So here's just an example. This is a large wind farm laid out in a grid. Turbine 10, far to the right. The blue sector is the allowable wind directions according to the IEC standard. So the turbine on the far right, fantastic. We've adjusted that turbine. We have lots of opportunity to follow the IEC standard here to get nice measurements. Turbine 2 is in the middle. If we make any changes there, we just have that narrow, strictly speaking, that narrow little blue wedge is the only thing that we, by the standard, are allowed to use. Tough to tell a customer we can't measure a performance improvement that we made there. So, how do we come up with a standard that deals with that? Just another challenge that we have. This is another example we have that this is one of my favorite questions we get from customers. We did some modifications at a wind farm. We tried to set it up that we had some control turbines that weren't adjusted by us and some that were. This is an example of a turbine on the right that wasn't adjusted by us. As far as we know, no modifications were made to this turbine. Customer isn't necessarily diligent about what's happened to their turbines. They said, wow, we can see great improvement on these turbines. And we have to explain to them, we didn't do anything to this turbine. But they look at this power curve and they say, fantastic, this looks great. Can you make all of the turbines look like this? This orange line. A lot of times that line is due to some kind of nacelle calibration issue or nacelle transfer function change. we've occasionally seen it exceed the BETS limit. And now we have to explain to a customer that we can't make all the turbines look like that. And that what they're seeing isn't actually a real improvement in the turbine at all. It's just a scaling of the x-axis from the wind speed measurement. So this is more of a customer perception issue that also needs to be addressed. Other customers understand, that this isn't reality. So I'm not blanket stating all customers. We have this wide spectrum where some people say, make them all look like that. And a lot of times what they want us to make them all look like isn't a feasible thing. I think one turbine we had such a bad nacelle transfer function relationship that it was generating 1 megawatt at like 4 meters per second, and according to the power curve, not in reality, but, they didn't have the understanding to say, wait a minute, that makes no sense at all. So there is, for some customers, a fundamental understanding that needs to be addressed. Others completely, on board. They're like, oh, this is a nacelle transfer function issue. We'll go fix that. And here I just made up a quick example of 3 different changes to a power curve. One, I boosted region 2. So this is completely hypothetical. I boosted everything in region 2 by 2%. That's the orange line. For the other 2, I shifted the nacelle transfer function by 1/4 of a meter per second to the left and 1/10 of a meter per second to the left. And on the bottom just shows the perceived percentage improvement in the power curve for each of these. So you can see shifting a power curve by 1/4 of a meter per second to the left starts to look like the power curve is improved by 10% almost everywhere. Even just 1/10 of a meter per second correction is about a 5% improvement. So this real actual performance improvement of 2% doesn't look that great compared to just shifting the nacelle transfer function to the left. So that kind of challenge is something that, managing customer perception is, what's really a performance improvement and what just looks pretty on the power curve. So one thing I'm hoping we can get from this working group is, a standard that helps customers understand this and be able to measure power performance on their own as well. So we don't have that issue of trust between the recommender of the improvements and the measure of the improvements. I forgot to slap. This is just some example nacelle transfer functions for different OEMs. These are 4 different OEMs. The one in the upper left, they have different table lookups for nacelle transfer functions based on software anemometer types. Some people might have a quadratic relationship for their nacelle transfer function. Another OEM just has single table relationship. And a lot of OEMs just have a linear relationship. Some have bounced back and forth between different things. So there's not necessarily a single way to improve a nacelle transfer function. If you just have a linear relationship, it's very hard if the wind speed measurements are different. The table is much nicer for that kind of thing. What we've seen is it's blindly applied to every turbine on the farm. They're like, here's the table lookup, just use it for the whole farm. So we don't see turbine-specific nacelle transfer functions, in our experience. So what could help? I've mentioned this a couple of times. It'd be great to have a robust, reliable, transparent, and straightforward approach to quantify performance improvements. Much easier said than done. I know everybody's tried to find a way that works in the real world. So what I'll be talking about next is this measurement consensus method. Is just one way to help estimate a more likely value for the measurement, any measurement. I'll be talking about wind direction and wind speed, but you could use it for any signal you would like. And we're going to base this on the behavior of nearby turbines. So similar idea, this is sort of baseline motivating work for Windesco's wake steering swarm solution that we have. So we're looking for a more cooperative approach among the turbines rather than greedy, where every turbine says, this is my measurement of wind direction. We're going to start to look for cooperative measurements of wind direction. And we're going to try and find a more likely measurement value. So NREL did a lot of this initial work on this. Jennifer Ananini did. But then, Windesco, we did some joint research. We had a wind farm that we are now currently doing swarm on, our wake steering. But we did some, base research on this to look at these wind direction consensus methods. The motivation for that was to say, is there a way we can correct nacelle position measurements in real time so that the turbines have a more accurate representation of wind direction and therefore would yaw less? So I'm not going to talk so much in this about that idea for an implementation. That was a yaw controller with a deadband so that the turbines wouldn't yaw as much, and they showed some energy improvement. So I am going to show the results from that, just not the method. At the end of this, there are links to the presentation I took the rest of these slides from and the original paper if you're curious on how it's implemented. Not going to show any math here. There's a lot of math, but this is, what this looks like and how it gets implemented. So typically, wind turbines operate individually, optimizing their own performance. And the yaw position or the yaw error of the turbine is just determined by the wind direction sensor that's behind the rotor. So it has its own measurement issues there as well. And sometimes measurements are noisy, sometimes they're susceptible to different things. And so this can lead to yaw misalignment of the turbine. This is really talking about the dynamic yaw misalignment, that instantaneously the turbine is not aligned with the wind. When turbines reach a certain threshold, different for every OEM, of what's considered not pointing into the wind, they'll then yaw back into the wind based on this measurements. There's some kind of time periods, maybe some kind of averaging. Some OEMs are very quick, probably could relax their yaw controller a little bit. Others are very lazy, very slow. And they have different thresholds for how, 1 minute at 10 degrees off, 30 seconds at 6 degrees off, as a general rule. So I had not realized these slides are dynamic. Cool. So misalignment can occur across the wind farm. Each turbine at any moment in time is seeing its own misalignment to the wind. Here is an example showing the wind is just blowing left to right, but the first turbine's somehow misaligned clockwise. This turbine behind it's misaligned counterclockwise, and so on. This front turbine here is in the second row is pointed right into the wind, and so on. So instead of having all of these turbines trying to guess the wind direction here is a straight west to east, but each turbine has their own best guess of where the wind is coming from. Now, some of that may be driven by topography, so that's why this method is great but not perfect. So the solution that NREL proposed is to do some increased communication. So the reason they partnered with Windesco is we have lots of real world data. So in this case, this is a 58 turbine farm. And on the left, we're showing some real wind direction measurements at a moment in time. Now, fortunately, in this case, this site, the nacelle directions are calibrated to north. This site has wind sector management, which means that they have to shut down when the wind's blowing from certain directions for loads reasons. So they're very diligent about making sure that when the nacelle says it's pointing north, the turbine's actually pointing north. The end result we see, and we'll talk about how this comes about, on the right, we've estimated a wind direction. So rather than on the left, we see each turbine is pointing in a completely different direction. This bottom row here, there's one turbine that thinks the wind is coming from west-northwest. All the others are saying north-northwest-ish. We run this consensus method, and now we get much better estimates of the wind direction. And you can see that these do still vary cluster to cluster. This cluster in the northwest corner, wind is coming north-northeast-ish. But, just the cluster just to the southeast of that, the wind looks like it's coming from the north. So there is some sensitivity to geographic location, and that's because this wind consensus method, has a distance weighting that turbines that are nearby count more heavily towards inputting the information that we care about. So the other thing that's nice, and we'll see some examples of that, is this can also correct for faulty or noisy sensors, which I think is a great opportunity for this method to say, hey, this sensor is measuring a wrong direction. You know, maybe its north position needs to be correct, or if you use a different thing, maybe it's, you know, anemometer needs to be recalibrated in the cell transfer function, things like that. But one thing it does not do, in and of itself, the consensus methods won't correct for things like a north alignment. That still needs different approaches. This is just saying we want all the turbines to agree on a direction for the wind. It may not be an accurate direction for the wind, but we're just trying to get some precision. So you think about the target. You know, you want small clusters. If they're in the bullseye, that's great, but small clusters are better than a scatter approach. So north alignment is a different problem. This doesn't fix that problem. And the other requirement is that you can't have turbines with this drifting the cell position, because now you're trying to correct positions and you're not quite sure what's going on because everybody's truth is different from moment to moment. So a little more detail about this data set that we have. This is a very large wind farm. These are all 2.5 megawatt turbines. These turbines are calibrated to the north. We've collected 1 hertz data, and you know, the cell direction, power, yaw error, wind speed, and pitch. For these turbines, we can also calculate 10-minute or 10-minute, these different time intervals, 1 minute, 5 minute, 10-minute statistics from this 1 second data. We provided 8 months of high-speed data. At this site, we do have a Met tower that provided information on wind speed and wind direction. This Met tower is also maintained and calibrated, so we know we can trust these measurements as well. That's not always the case at farms we've encountered. So here's an example where we see turbine sensors can be wrong or fail. You know, in the circle here, on the left, we can see one of the turbines is saying this wind is due north. All the others are saying it's mostly a southerly wind. We run this consensus algorithm, and now we've estimated that the wind is most likely blowing from the southeast-ish. So here's an opportunity. You can look and say, well, the measurement is significantly different from the consensus value, so there must be something wrong with that sensor. That's a really nice benefit of this method, is that you could identify faulty sensors from that kind of comparison. And you can see that, you know, even in the bottom row, on the left to the right, wind directions are much tighter. You know, you can see the bottom row, the upper left turbine in the bottom row is pointed southeast-ish, but then later on it gets corrected more towards a southerly direction. And you can see that throughout the farm, that there's this kind of correction to make the turbines appear to be more pointing in the same direction. Now for this experiment, one of the requirements was to have a reliable Met tower, and we do. We can compare the actual Met tower wind direction estimate to this consensus method, and we see these match up pretty well. The Met tower measurements in blue, the consensus estimates are in red. You know, they match pretty well. For something that's averaging across the whole farm, these are doing a pretty good job of estimating a true wind direction. So that's an encouraging result to see that, hey, we can get, you know, some nice, good wind direction here. Again, we still don't know what's happening at each turbine. We're just trying to give better estimates of what's likely happening. So some challenges and some other alternative concepts that NREL and Windesco looked at. Because this method is relatively complex to implement, it's not impossible, it's just complex compared to these other methods. So they evaluated some simpler methods to say, you know, do we even need to be doing something this complicated? So they did a straight up averaging across the farm, some weighted averaging where now we're going to weight distance as part of our averaging. And then they did a clustered weighting average where they said, okay, now we're just going to look at clusters and just weight for a given cluster, what does the wind direction look like? So this is heading more towards a consensus method. Rather than weighted averaging across the whole farm, you just do this weighted averaging for different clusters. And now let's compare those results to the consensus methods and see what we get. So how does this feel different? Now we're going to get a little bit into how the consensus method works. So we get wind direction measurements at each turbine on the left there. If we're going to go averaging along the bottom path, you just average across whichever turbines you've selected for the averaging, give them the appropriate weighting if there's a distance weighting involved. And now you have a new estimate of the wind direction. So the averaging method is, you can consider that open loop. There's no feedback. The consensus method, similar thing. We compare the estimate to the measured wind directions. Then we compare that estimate to the wind direction of nearby turbines. Now here's where the correction would come in if those are different. We then update our estimate, and we just repeat that process until we get some convergence on a solution. We're like, okay, this isn't changing any further. And then we would output an estimated wind direction. So now again, for this wind farm, we're going to average the wind direction. We did a circular average, so we made sure we accounted for stuff going between 0 and 360. So just the averaging, really fast to do. Some disadvantages, it doesn't take into account local terrain, which we're doing by using just adjacent turbines. So it weights far turbines as much as close turbines. And it's harder to catch outliers and faults. We'll see in the results. This weighted average method, still very easy to compute. Turbines that are closer get heavier weight. Some cons, it's still difficult to catch outliers and faults, and we'll see when we look at an example. This cluster weighting average is starting to move towards a consensus method thought. Again, now we're going to only select turbines within a certain distance, so just 20 diameters or whatever. Again, still easy to calculate. Same kind of things. Again, still may not catch outliers. This does a little bit of a better job, but you still may not catch outliers. Mostly you can't catch outliers because you don't have a lot of turbines. If you have 7 turbines in your cluster, which one's bad? 2 of them are bad. It's hard to decide that they're bad. This cluster averaging is iterative, so that's an advantage of it. Because it heavily weights nearby turbines, it has some local effects. It can catch outliers. Disadvantage, it's difficult to implement, and it's slower, right? But if we look at these calculations, half a second versus 100th of a second, when you're talking about controlling a wind farm, half second's not a big deal, just in terms of giving feedback that's reliable for people to do things. This is, so they made a synthetic example, just a small wind farm, 6 turbines, labeled them counterclockwise, turbine 0 is on the left, counterclockwise up to turbine, I guess they did a little zigzaggy thing. Turbine 4 and 5 are different. We're going to pick which turbines talk to each other, so you can see here is just some decision. This is part of the algorithm to decide which turbines get included. And they've introduced a faulty signal on turbine 0. So the other 5 turbines are measuring the wind direction from the west. Turbine 0 says the wind is coming from the south. Now, if we go look at how these results behave, in the middle top here is the scenario. Turbine 0 has a wrong wind direction. We go right to the bang on the right side there. The consensus method, all of the turbines are now corrected to go in the right direction. Equal average in the lower left. You can see all the turbines are pointed in the same direction now, but it's not the correct direction. The faulty measurement from turbine 0 has now been averaged across the other turbines. So now instead of having 1 wrong by a lot, you have 6 wrong by a little bit. Weighted average is a little bit better. The incorrect measurement is just affecting the 2 adjacent turbines, but you can see turbine 0 still has a lot of misalignment to the wind direction because it's only being corrected by 2, not all the other 5 turbines. And then the cluster, again, it's even worse because now we're only considering a few turbines there as well. There's no weighting from the other turbines. And the bar chart in the upper left just shows the mean absolute error, that the consensus method is far superior, then the average is the next, and the weighted averaging cluster average. So now if we start thinking about how many turbines are good for a cluster. So this plot just shows if we do clusters, we have some control over the size. So that's the yellow line up on the top. The green line is a consensus method. How many turbines do we want in a cluster? And then the average and the weighted are dots because they're considering the entire farm. We aren't doing any clustering there. So we can see the consensus method's great. If we have smaller farms, up to about 30 or 40 farms, it's still significant. But as you get higher and higher, the methods start to get a little bit closer for results. So huge advantage for smaller farms, giant farms, not necessarily as much of an advantage. So now that NREL and Wendesco went into this hypothetical experiment on what could we do if we designed some kind of yaw controller to take into account this consensus wind direction method. And so now they take this modified wind direction at each turbine and subtract the wind direction actually measured by the turbine. And that's going to give us an error in our wind direction signal. So they did some calculations for turbines with high error. How often does that occur? Turbines with low error. They use two different power curves. And then they look at what energy could have been produced versus what was actually produced. And the difference from that is they're calling their AEP gain. So they're looking at the energy that was actually produced, generating a hypothetical estimate of what energy could have been produced, and saying, could this new yaw controller work, to improve energy? And this is showing here the x-axis is time scale. So what kind of averaging do you need to do to realize which kind of benefits? And then the y-axis is just the potential average AEP gain for turbine. They did this for the 4 different approaches that we talked about. Again, the slides that I link at the end explain this in more detail. I didn't want to get involved in that because we're really talking about just the consensus method. And you can see that the consensus and the average methods actually produce pretty similar gains. The weighted and the clustering don't necessarily do as well, but even if you went with the clustering method, you'd still get a 1% AEP improvement. So just doing something besides letting the turbines operate on their own understanding of the wind direction can actually help improve performance. And it looks like really just using 1-minute data, 1-minute averages is sufficient. We still see benefit with 10-minute data, which is great because a lot of farms, it's challenging for them to get the high-speed data to calculate 1-minute statistics. So even if all you can get from a farm is 10-minute data, this kind of approach could work. Now, this is all hypothetical. It's really easy to say this would work. The implementation of this is a much more challenging thing. Again, not the point of this conversation. So I wanted to bring it back to what I suggested at the last meeting, that this consensus method could be used to help improve wind measurements. So this is from a 50 turbine farm. One turbine has an incorrect nacelle transfer function. It's the blue one. Just normalize the power to see, but you can see this is producing 60% of its power at 5 meters per second. That's a fantastic turbine. Not actually realizable. But what do we do? How do you decide how do you correct that power curve to maybe make all our analysis from this turbine at least useful? If you calculate derived statistics from this, like a tip speed ratio, a power coefficient, things like that, all of those measurements are going to be wrong because you have a bad nacelle transfer function. So you can't even calculate, derived variables from this because your input is wrong, the wind measurement is wrong. So can we make this more reasonable that perhaps at least we can calculate those kinds of things and see if there's some kind of issue or opportunity we can define. So in this case, I applied, I did 2 things here. The top row shows the wind speed, so the power curve versus the measured wind speed, and then I did a density corrected wind speed on the right. Clearly still a bad nacelle transfer function. Correcting for density doesn't make it much better at all. I then applied the consensus method to both approaches, to the wind speed signal and the corrected wind speed signals. And now this power curve looks reasonable. It's actually put it on the far right side of all the other curves. All the other turbines are in gray here. And so you can see, rather than being this giant outlier, it's now actually showing it's performing on the low side of the other turbines. I don't know if the consensus method is strong enough to say, yes, this turbine is now underperforming compared to others, but it at least puts it in the ballpark with the other turbines that we can calculate downstream statistics, TSR, CP, things like that, and maybe start to evaluate those parameters with a little more confidence. So in summary, consensus methods just used to help correct turbine measurements that may be outliers. I think it does a great job of that, can be helpful to identify outliers. Still just an approximation to the true value. That turbine, how much is its terrain unique from other turbines even nearby? This was in a pretty open area, so it's probably much better than if you were like in the mountains in California, where one turbine is 20 meters higher than the next closest turbine. Again, so for this specific example, for the wind direction measurements, they'd come up with this hypothetical minimize yawing to help optimize performance. And so for wind speed measurements, this is an improvement over doing nothing. And it still may not be accurate. A great thing to do would be go get a LiDAR or Met Tower to confirm accuracy like we did there. We haven't done that. We're not using this necessarily to do anything, but if you wanted to have more confidence in your measurement, you'd want to go measure with a LiDAR or something like that. And now you defeat the purpose of trying to be a SCADA only, data analysis company. For experiments, that might be the nice thing to do. But that's, so that's the consensus method approach. Paper is fantastically written. The slides give a little more background on what's going on. So I put some topics for discussion. I don't know. That's my present. Oh, and then after that is just the references. There's two here. I think you will send out the presentation, so you'll have these links you can click on. But that's my presentation. So I guess we're open for questions or discussion.
Right. Thank you very much, Jonathan, for the really insightful presentation. As Jonathan mentioned, after the meeting, the recorded session and also the set of slides will be placed on the workspace we have. I sent out the email to list with the dates, and there's slides, there's recording, and as we progress, it's always at the same place. So, you're welcome to kind of go back to refresh your memory of what we discussed and about the slides and other things. Just in case other folks, if you know of missed the meeting, they like to take a look of what being discussed, then that would be the place to go. Do you have any questions for Jonathan and for his presentation? Akshay.
Hi. Jonathan, one question about like the kind of corrections that you have typically seen you need to do when you look at the estimate versus the measured wind direction or the reported wind direction from the turbine. Are these typically some kind of systematic bias in wind direction, or are these errors more random?
Yeah, so like I said, we don't necessarily use this for anything, but yeah, when I see issues with like wind direction, we don't focus much on wind direction usually. Most of our solutions try to be wind direction independent, just because of the challenges with waking and things like that. But as I said, we've also seen some OEMs have no control over their wind direction. So you could have a turbine pointing, fixed in one direction, and if you just watch the nacelle measurement, it'll change, 20 degrees. So, for a while we like, well, let's try and fix that, but how do you fix that? And then, the other turbine is changing 20 degrees in the other direction. So they may start the day aligned, At the end of the day, they're measuring 40 degrees different, but they're still pointed in the same direction. So, you know, we haven't necessarily made, just because we're trying to be OEM agnostic. When you have an OEM that you can't rely, you know, it's hard to do that kind of thing. We've done custom things to check, like if a customer has a wind direction dependent curtailment, we'll do a little more focus on that. But those sites are usually pretty good about calibrating turbines on a regular basis so that they're pointing north, because they want to make sure they're in compliance with their curtailment, and they don't want to be not operating when they can't, right? So, you know, customers, they get constraints on them, and a lot of them perceive them as like, I want to make sure I don't violate my constraints, but I want to be operating as much as I possibly can. You know, like an example is bat curtailment, right? They can't operate at 6 meters per second and under.
Mm-hmm.
They want, if they're at 6.001 meters per second for a wind speed, they want to be operating, right? You know, they're like, they don't want to injure wildlife, but they also want to maximize their performance opportunities. So those customers who have those constraints are usually much better about diligently maintaining their nacelle transfer functions, their wind speed measurements. And from the wind speed side, it's just like the example I showed there, there's one turbine at the site. The other example I showed, I think the customer had a software upgrade in the middle of our experiment, because almost all the turbines at the farm have a new looking power curve. So, you know, we don't use wind speed for our energy measurement comparisons, so that's helpful. We're not susceptible to that, but the customer's also newer to the wind industry, so explaining to them that just because your power curve looks better doesn't mean you're getting more power is a challenge. Does that answer your question? I didn't mean to be too vague.
No, yeah, it does. I mean, at least the one
Okay.
you mentioned about the problems you saw in terms of nacelle position measurement with the yaw encoders. The other one I had was, I quickly caught you said you don't use the wind speed at all in farm performance quantification. I mean, what is really an example of an unbiased observation that can be used as the x-axis or the independent variable for park performance?
Yeah, so we have you know, I don't want to go into too many details, but we do a side-by-side comparison. You know, it's a little more advanced than that, but it's a side-by-side comparison. The only thing we use wind speed for is to make sure, among other environmental parameters, is to make sure the before and after periods are similar. Right, like I talked about that example at the beginning, that, you know, if the wind's from the east in the summer, from the west in the winter, you really don't want to make changes in the fall as that wind's transitioning, because then your before periods from the east and then your after periods from the west, and the terrain might be different if the wind's blowing from the east and the west. You know, now your waking behavior is all different. So we try to avoid that. The other challenge I didn't even mention here is, if you have a farm like that, as soon as you find an opportunity to improve the farm, the customer wants to implement it. It's difficult to say to them, well, you know, September is the worst possible time to make an adjustment. Can we wait until November? Because as soon as they feel that there's an opportunity for improvement, they're not interested in helping us have a robust before and after data set. You know, they want the money. So, you know, how do you measure energy when you have those challenges? And we're doing our best. And I think, you know, last week, you know, or last time, we talked about some methods that I thought were helpful for that kind of thing, you know, shaping your inputs to improve that. So I think there's opportunities that exist that we haven't necessarily incorporated for that. But I was very excited the last meeting, because I think we did talk about some of those things, or some of the materials that were linked to point in that direction of shaping your before and after time periods. That, you know, it's not like it's, you know, August 31st, the wind's from the east, September 1st, it's from the west. You do have some overlap as the winds transition. So how can you just select from that data to make things happen? You know, there's still opportunity to do that we've started to explore independent of this, but I was more excited and motivated after the last meeting for that. So yeah, we do a side-by-side. You know, that's why I'm here too. You know, I'd really like to see this group come up with some great method that is sort of not like, oh, Windesco fixed your thing, so Windesco measured it. We have had customers come to us and say the OEM made a change, they measured it and said it's better. We don't feel like it is. Whether that's just an OEM, we don't trust our OEMs, or they just aren't observing it in their bottom line. We've been asked to evaluate things like that. So there's definitely challenges of trust and transparency in measurements, and there shouldn't be, because I don't at the human level, people aren't doing things like that, right? It's just, but how do you, like, one time this is a story I took to heart. Like, we predicted a 1% improvement, and then we measured a 1% improvement. And the customer, instead of being excited, said, well, isn't that convenient that you measured exactly what you predicted? So we were like, well, that's what happened. But it was just,
I think one of the fundamental, sorry to cut you short, one of the fundamental difficulty is really people cannot do a controlled experiment, right? All the experiment to some extent approximation. There's things you cannot, you cannot really do, even you couldn't replicate the kind of condition in the wind tunnel. And because there's no wind tunnel to that kind of size.
Right, and our method is sufficiently complicated that it's hard, as I talked, across our spectrum of technical capabilities for our customers. Some customers have, a performance engineer who can kind of understand what we're doing. Other customers don't, and that, they either believe us or they don't. It ultimately comes down to, are they willing to say, okay, we trust your answers, or we need to see how you did it, and then we try to explain it to them, and there's just a technical capability challenge there. Not in a good or bad way, it's just, they just don't have a performance engineer who thinks about these things on a regular basis. So it's some trust, and it's hard to do, right? There's a little bit of art to performance measurement. It's not just do this, that, because it's not a controlled experiment, right? So which data do you keep? Which data do you not keep? Doing that input shaping that, I really think we talked about it last time, right? Just, shape the data set. It's something that I think someone could understand. You're like, well, we want to have this kind of distribution before and this kind of distribution after, so we're just going to pick those data points. That's easy to understand, that those kinds of things are helpful and can hopefully lead to somewhere that you could just say to somebody, hey, it'd be perfect world, they go to a website and they can plug in their data, and there's some Python thing that runs in the cloud that gives them a result, and they're like, oh, okay, cool. I ran my results without Windesco touching my data, and I see that there's performance improvement.
So Jonathan, one thing I want to ask you related to your presentation. At one point you mentioned about the scatter data you guys used is 1 Hertz in frequency, and then to also use the industry standard 10 minutes. What is your thoughts on the sensitivity of different methods to this time resolution of the data? Do you typically use a high frequency data, or you typically just use the 10 minutes data?
So a lot of our analytics, that we do when we analyze turbine performance, we use high-speed data. It varies from customer to customer, whether it's 1 second or 10 second or 20 second. But for power performance, we usually use 10-minute data because we're looking at a bigger picture there. That the consensus. So if I ran, like when I ran that consensus method on the wind speed, that was just with 10-minute data. To me, consensus method is looking at a bigger picture. It's not instantaneous changes. That 10-minute is a fair representation of what's happening. For our own analytics, we do a lot of high frequency data analysis, but measurement is usually done at the 10-minute time scale just because that's a fair comparison for 10 minutes. Turbine A, the wind gust might hit them a little bit earlier than turbine B, and if you're too fine a resolution for time, you're going to acknowledge, it's just going to make things challenging that the 10-minute seems to work better for performance.
So from the academic point of view, from an analytical point of view, do you see a difference if you apply pretty much the same method to different resolution of data and see a different outcome?
No, so that's what that one plot that I showed. Let's see. Oh yeah, so a little bit. The one plot I showed for the performance of the different methods showed that for consensus method and the averaging, they were pretty insensitive to time, to the time window. The other two methods, the weighted and the clustering method, were more sensitive to time. I think a long time ago we decided 10-minute was fine and haven't, we just did a study a long time ago and just saw that 10-minute was simple. The nice thing about using 10-minute data is it's faster, right? I can go through 8 months of 10-minute data a lot faster than I can go through 8. It takes a long time to even load 8 months of 1 second data. So we found that there wasn't sufficient difference, that the 10-minute works fine.
And any other questions for Jonathan?
This paper, would you be able to share a link?
Yeah, so in
the slides,
the last slide has links to both the technical paper and the presentation that I took the second half of the slides from. So you said he's going to put the presentation in the workspace, and then the link will be right in the presentation for both papers that I base this on.
Yeah, I will post the slides after the meeting to the WidiWin workspace, and then from there you can click the link. I clicked the link myself yesterday already because Jonathan gave me the slides yesterday. So yeah, it works.
And it works good. Okay, cool. Yeah, and those are open source papers, so it's free to download. Nice thing about government work is that they have to share it with everybody. So it's
excellent.
Yeah.
Well, the same thing about academia, right? We in the university supposed to publish. Sometimes behind the paywall, but we are free to distribute for academic purposes.
Yeah, I find people, even if their stuff's behind a paywall, if you contact the professor or whatever, they're happy to share.
If they put before paywall, we cannot really put on the open website, but we can give a single copy to whoever requests that.
Yeah.
Yeah, government is required to make it free access.
Right.
So we are a couple of minutes away from the hour, and I think our April meeting, the plan is Philip from Big Pro. If Philip, you are here? I see a Philip in the meeting. I'm not sure it's the same person.
Yes, I am here. Yeah, I'm also on baby duty at the same time. So, but yes, I'm here listening in.
Great. So, is that are you still able to do a presentation for April meeting?
Yes, I should be.
Okay,
yeah, and again, it's a sort of in some ways a similar topic about the difficulty of these wind speed measurements changing and how to calibrate that. Maybe a slightly different method on that, but yeah, similar kind of issues, I guess, that we're seeing in industry that we're trying to tackle.
Very important. Yeah, it's a very important issue. We should kind of concentrate on that to discuss that for a while. If we don't have any guest speaker for May meeting, and I plan to ask one of my graduate students to do some of the initial analysis, use the data we share, and to, for either implement some of the method we reviewed and kind of try some ideas to be discussed here. So that way we can kind of doing the discussion and showing the analysis and then kind of iterate the forward to see the pros and cons and probably will motivate more discussion going forward. And but I think for the April meeting, we will proceed with the plan with Philip given presentation. So any other things? And once again, thank you very much, Jonathan, for the very interesting presentation and for all the great discussions in the meeting.
Good, thank you.
Okay, if no other questions, I look forward to see you all in a month, and I will send the email after I post the the recording on Jonathan's slides. Okay. You have a good day and good evening.
Thank you.
Thank you.
Thank you.
Thanks, everyone.
Bye.